addition to the task of handling millions of travelers every day, today's airports face challenges related to air and water quality, noise pollution, energy efficiency, and safety and security. For a moment, let us imagine we had $3 million to address these critical issues using hydrogen technologies at the Columbia Metropolitan Airport in Columbia, South Carolina. Although a good design will address the challenges at the Columbia Airport, a truly great design will also have key elements that are applicable to other airports around the world. The hydrogen technologies and systems selected must be commercially available and possible to implement for practical, real-world use by 2009. To better understand the project scope, let us look at the total number of operations at the Columbia Metropolitan Airport during the past 4 years. This second graph shows the percentage of airport operations that were on time at Columbia Airport. Unfortunately, the trend is downward, with the percentage of on-time operations in decline. We all know of applications where hydrogen technologies are more energy efficient and reliable than conventional systems, thus having the potential to mitigate the critical issues related to safety and security, energy efficiency, along with noise, air, and water pollution. The design as a whole can be divided into several smaller, distinct areas of application. These application areas are hydrogen gas acquisition, auxiliary power generation, energy savings power generation, hydrogen fuel cell vehicles and remote devices, and technologies dedicated to public education. Liquid hydrogen was selected to be purchased to reduce initial capital costs and to maintain a flexible, evolving hydrogen system. Hence, as the hydrogen infrastructure and technologies improve, the design will easily adapt to the most economical technologies available. The proposed hydrogen fueling station involves a leased liquid tanker, vaporizer, and a dispenser. This system includes an onboard compressor and high-pressure storage system capable of fueling up to 50 kilograms of hydrogen per day at 350 bar pressure. After analyzing the operations at the Columbia Metropolitan Airport, the design team observed that the airport has experienced an increase in power outages that could potentially have a negative impact on the airport operations. To address this critical weakness, the design team selected a 30-kilowatt auxiliary power system using a stack of 6 5-kilowatt fuel cells. While this system could serve a number of different areas, the design proposed that the airport computer network be protected first. To function as a backup power unit, an additional module that includes batteries will be used to bridge the downtime between a power failure and fuel cell warm-up time. The dependability of the fuel cells and the backup power unit in general will assure that no data will be lost in the event of a power outage. To help reduce airport on-peak power usage, another fuel cell system was selected. The goal of this equipment is to reduce on-peak loading by approximately 200 kilowatts and to provide backup power during emergency situations. This system could be fueled with either natural gas or landfill gases, as it utilizes steam methane reformation to generate the hydrogen for the fuel cell stack. As part of the design's educational and marketing component, both airport employees and passengers will have the opportunity to learn more about hydrogen energy technologies via highly visible applications. The design includes the use of hydrogen technologies to address several specific personal vehicle and remote power applications. The most noticeable hydrogen vehicle included in the plan is the proposed hydrogen internal combustion engine shuttle bus. This vehicle, which could potentially be leased from Ford Motor Company, will be used to shuttle passengers to and from downtown Columbia, as well as the Amtrak station. The use of hydrogen in this internal combustion engine can be seen as a bridging technology, while the fuel cell technology is being further refined for transportation purposes. To meet the needs for the demonstration of a hydrogen forklift, fuel cell power modules were selected. These fuel cells have been designed such that they are a drop-in replacement for the traditional battery power systems used in electric forklifts and are fueled by hydrogen stored at a pressure of 5,000 pounds per square inch. These power modules are capable of delivering 21 kilowatt-hours of electric energy at 48 volts, adequate to power a standard Class 1 forklift. The advantages of this technology are reduced fueling times, elimination of space for charging stations, extended runtime between fills, and an emissions-free power source. A multifunction utility service vehicle was selected to be used in the terminal. This vehicle could also provide both AC and DC electrical power, enabling it to act as a generator that provides off-board power to various equipment both inside and outside the airport. A hydrogen fuel cell scooter will serve as an additional roaming advertisement to today's hydrogen possibilities. The zero-emission scooter can reach up to a maximum speed of over 30 miles per hour and has a range of approximately 37 miles. The scooter's fuel supply is delivered via a metal hydride canister that is simply exchanged for a new canister at refueling. The design includes fuel cell power units for remote power applications such as communications equipment for early response teams, small electric tool operation, or any other application that requires light, reliable, portable electric power. These power packs are compact in size, lightweight, environmentally friendly, and have consistent runtime and smaller recharge times compared to conventional battery units. A special public education display will be located near the ticketing desks in the terminal. This hydrogen technology display will be powered by an autonomous power supply from a PEM fuel cell. In this case, the hydrogen will be produced from an electrolyzer capable of producing 4.31 kilograms of hydrogen per day. Visitors to this hydrogen education display will be invited to use the computers around the column or charge their own computers. The hydrogen equipment will be placed behind a plexiglass barrier, permitting the visitors to observe these hydrogen energy technologies in operation. All application of hydrogen technologies are assessed to be economically viable and doable based upon the following analyses. The proposed business plan identifies a mixture of capital investments as well as lease agreements of equipment. The use of leased equipment has the potential to reduce the initial capital outlay while creating flexibility to change to emerging hydrogen technologies. The hydrogen cogeneration system represents the largest expenditure with 37% of the total budget. Major failure modes posing the greatest risk to the airport were identified as fire or combustion of the hydrogen, operator error, natural disaster, hardware failure, power outage. From the analysis, fire and operator error were estimated to be the highest priority items to address. Adequate safety measures will be designed and implemented to avoid these risks. Some of these include proper signage as well as more advanced solutions such as smart cards and infrared sensors. One of the advantages of the hydrogen technologies is that they are cleaner compared to traditional systems. For instance, here is a comparison of emissions for the proposed cogeneration unit. A well-to-wheel analysis was performed using the GREET, Greenhouse Gases, Regulated Emissions, and Energy Use in Transportation model, since fuel pathways should be carefully examined for their intended energy and emission benefits of advanced vehicle fuel systems. Replacing an electric battery with a fuel cell potentially can eliminate the source of heavy metals harmful for the environment. The use of a fuel cell power generation system instead of diesel generators can also lower noise levels. The hydrogen educational plan focuses on both the airport staff and the general public. The marketing will be done through advertisements, demonstrations, newsletters, brochures, and websites.